Okay, next we're going to talk about equilibrium. And so just like 1D, we're going to take our rod here. We have an x-axis. And we're going to assume that we have some distributed torque on this. So that might look something like that. We'd have a bunch of arrows. And just like when we had our B, now we have a T. So this is going to be our distributed torque. So it's a torque per unit length. And we assume that this has some length and some boundary conditions. We don't have to worry about those quite yet. But what we're going to end up doing, like we've done some other times before, is we're going to take a little slice out of there, and we're going to look at the forces that are acting on it. So here is going to be our cross section. This is going to be delta x, so it's just a little slice of our rod or our shaft here at a distance delta x long. And we have some internal moments, so we can start on this side. And so these are going to be internal torques, so it's a moment, and that's what the double arrows there are meant to indicate. So it's a torque around that axis, and it's going to follow that right-hand rule. And we would say that this is going to be the internal torque at x. And if we think about the other side, we're going to have some torque on that side as well, and that's going to be at x plus delta x. If x is on this side, that's going to be x plus delta x on that side. And we have some value that's going to be t. That's going to be t at x. And now what we want to do is we want to take, I guess I should give this an axis still. This is the x-axis. And so we can do equilibrium of this section. We'll do that up here. And so I'm going to take the sum of the moments again about the x-axis. And we're going to say that counterclockwise is positive. And we know that that's going to be equal to 0. So we know 0 is equal to, well, this arrow, double arrow, is pointing in the direction of x, so it's positive. That makes sense, right? So we're going to have t of x plus delta x. This arrow back here, that's pointing opposite x, so it's going to be it's going to end up being a negative moment or torque. So that's going to be minus t of x. And then the last question is what's going on with our distributed t, or little t here. And it's going to be it's a unit torque again. It's going to be acting positive in our picture. And so we need to take our unit torque, so that's little t of x times our length. That'd be delta x. If we want to get this little t all by itself, we divide the whole thing through by delta x. We get 0 is equal to t x plus delta x minus t of x, all of that over delta x plus t of x. Should be looking quite familiar. What are we going to end up with? We're going to end up with 0 is equal to dt dx plus little t of x. So the change in internal torque with respect to length is just going to be the opposite of our applied, our body torque, I guess, if you'd like, but our distributed torque here. And again, we did that by taking the limit as delta x approaches 0, and we could circle that. That there is going to be our equilibrium equation. And just like before in 1D, we're going to use that to derive our governing equation. And that's going to be on our next page.